So in this talk I will tell you about a theory of quantum gravity that I proposed 2 years ago, and that I claim is the theory, for reasons that I will outline in this talk. It's based on a new quantization prescription which defines a fake particle, or fakeon, and it can be used to get rid of ghosts. But you have to do something in order to get rid of them, and we'll see what you have to do. I and some students have been studying the theory already for 2 years, so I will also talk about some implications, predictions, and also about speculations. The Higgs boson could be a fake, and new features that this theory predicts in the classical limit. Don't think we will have too much time to talk about cosmology, but maybe some words on that. So the problem of quantum gravity is to make it renormalizable and unitary at the same time, and one way to make it renormalizable is by means of higher derivatives, because higher derivatives improve the ultraviolet behaviors of propagators. Propagators fall off more rapidly. But the point is that such propagators have a problem if you decompose them as sums of simple poles. At least one of them has the wrong sign in front. This leads to a ghost. Actually, that's what you think. Normally, that leads to a ghost. But here, it leads to nothing yet. Until you give a prescription, this is not a ghost. The key point, so, is having unitarity, because having renormalizability is basically easy, thanks to this trick, because you change the power counting. So let's analyze a little bit in detail what unitarity is. Unitarity is a statement that the S matrix is unitary. And if you write it as 1 plus IT by isolating the trivial part, you get this identity, which is known as optical theorem. Now, this is an identity that can be written diagrammatically, diagram by diagram, and it's possible to study it and to prove it. Well, with higher derivatives, you cannot prove that, at least if you use the Feynman prescription, but you prove a pseudo-unitarity equation where here in between, instead of having the identity, you have a matrix which has some plus ones and some minus ones. Basically, if you put states, in and out states of your Hilbert space, on the left-hand side you have the imaginary part of the diagram, and on the right-hand side you have something. Here you see, forget about this plus or minus one. Normally this is the relation where you have the completeness relation in between T dagger and T. Well, you don't have that. Due to these plus or minus signs, you will have that some states correctly will be multiplied by plus 1, some other states n will be multiplied by minus 1. And there is nothing you can do if you have this, because you cannot project them away. So W is your Fock space. Okay, you can reduce your Fock space to a subspace, getting rid of whatever you want. But here you see that is a completeness or a false completeness relation. It is what appears in between, and that you cannot decide. So a projection has to be consistent with something that goes on inside diagrams, because if you project something away from this sum, it is regenerated in the left-hand side as the imaginary part of a loop diagram. Let's see more explicitly the two simplest unitarity optical theorem equations. The first one is a very simple imaginary part of this diagram, tree diagram, and that is equal, if the optical theorem holds, you see T dagger T is non-negative, so you need to have something positive. And it has an interpretation. It's the cross-section for the production of the virtual particle. The virtual particle becomes real, you integrate over the phase space of the final states, and the modulus squared gives this imaginary part. So basically, you cannot project away a particle because it is hidden in the imaginary parts of other diagrams, and you would have an inconsistency. At one loop, you have the imaginary part of the bubble diagram that is related to the cross-section where the external particle produces the two virtual particles which become real now. And again, it's non-negative, so you cannot project them away and say they do not belong to your Fock space because they are ghosts, because that would become zero, but the left-hand side will stay non-zero. So let's see what's the point here. You have this propagator. As far as I'm writing this is not a ghost, this is not a physical particle, this is really nothing because it is divergent. You need a prescription, and the Feynman prescription gives you that. Is it okay? Yes, it is okay, because if you apply the Feynman prescription to this, put that propagator here, you simply get this identity, which is very simple, and the right-hand side is non-negative. You cannot change the sign of the propagator because that would change the sign of the left-hand side but would not change the sign of the right-hand side. So you would violate the theorem. So this, you see, is a non-linear equation. If you change the sign of the left-hand side, you cannot change the sign of the right-hand side because it's a square. So no matter what signs you put in front of your vertices, this is a modular square. They have no way to change its sign. But observe one thing. If you change both signs in front and in front of the prescription, then it's okay. If you change both signs, one here and one here, the optical theorem is okay. So one way would be you can argue to make these propagators, this one and the usual one, coexist. That's not possible, actually, and that has not been done for a reason. And with the physicist of La Sapienza, Uguaglietti, a couple of years ago, we detailed the problems that arise when both coexist, at least in a naive way. Basically, local quantum field theories generate non-local ultraviolet divergences. It's kind of awkward. You don't have the locality of counterterms, you don't have basic theorems, and the theory collapses mathematically. But there is one way to make them coexist, one only way to make them coexist, and that is this new quantization prescription, which I call the fakeon, fake particle. So let's see what it is. This is the propagator. Let me put a plus or minus in front, because I want to emphasize that everything I'm going to say works for both cases. Not only if this is a ghost, would-be ghost, and it will not be a ghost, but even if it is a true particle like the Higgs boson. So you have two poles on the real axis, and normally you integrate like that. That is the Feynman prescription. That is also the Wick rotation from the Euclidean, if you want. Now, multiply and divide by p squared minus m squared, like this. And ignore the numerator for the moment, because that is not a source of singularities. You see, you have doubled the poles. Split them with a small infinitesimal width. And then you are naturally led to this kind of funny integration path, where every pair stays on the same side. So the left pair is above and the right pair is below. This I call Lee-Wick integration path because it was first appeared in the Lee-Wick models. The Lee-Wick models are models where Lee and Wick claim to make sense of higher derivative theories, and the investigation I'm talking about now started with the initial objective that I had, that was to disprove the Lee-Wick models, because I could not believe that you can make sense of higher derivative theories. Well, the point is that Lee and Wick didn't complete the program, and so now we will see what the completion is, but their basic idea, this one, although not sufficient to define the models, is right, and it actually is so important that I think they deserve this recognition. So let's consider what happens in loop diagrams with this kind of propagator, which I call with this G plus minus. Basically, it is this object. It's a rational function, more complicated than the usual propagator, but apart from that, the story is the same. One crucial point is that when you integrate on the loop momentum, which I call K, you split the loop energy and the loop space momentum, you have to integrate on the Levy contour, okay? That tells you which residues you consider. That's crucial. Nothing will ever work if you integrate on Minkowski. This is not Minkowski. This comes from the Wick rotation, by the way. But we will have to say something about the Wick rotation in this case. So when you integrate on the loop energy, you will get the remaining integral on the loop space momentum with certain integrand which will be, well, not as simple as a rational function, but you know it's a rational function with square roots here and there, which are the frequencies. These are the square roots. Normally, you see in this kind of denominator, it's like having complex masses. But normally you don't have complex masses, you just have real masses. And the frequencies are the usual ones. Now we have to study the analyticity property of this amplitude. When is it analytic? In P, the external momentum. It's analytic anytime the integrand here is always regular for every value of the loop space momentum in the entire domain. If there is no singularity whatsoever, then this is analytic, obviously. But if there is one singularity, then analyticity breaks down. Where is the integrand singular? As usual, because this is the usual story, it's in singular when the external energy is a sum of frequencies for the internal particles. And normally, that's what you have. So the entire singularities of the bubble diagram, if you plot this for k varying on the entire domain, are two branch cuts. These two branch cuts. So these are the famous, well-known analyticity properties of the bubble diagram. But when you have an imaginary mass, these branch cuts blow up into extended regions, and your calculation doesn't make any sense. It makes sense mathematically, but it's not acceptable in any point of these regions. So if you calculate your integral there, here or here, wherever you want, you will have a result that is not analytic and not Lorentz invariant. And this is where the Lie and Wick stopped. There is a reason why the result is not Lorentz invariant, because you see you are integrating on this funny Lie-Wick integration path, which contains complex energies, and you insist on integrating on real complex momentum. So this makes no sense. Of course you're breaking Lorentz invariance. You have to deform this one too to complex values, and that will lead to the solution, at least one step towards the solution. So let's do it. Now, I can prove to you that if you deform this domain from R3 to certain complex domain, the entire extended regions shrink onto the two branch cuts. This is a good start. It's not the end, but a good start. And to describe what kind of deformation, in my papers you can find the explicit formulas, for example, in d equal 2. D equal 3 and 4 will not change much, but in d equal 2 it is very easy to visualize. In d equal 2 you have only one component, kx, and in the complex kx plane, the deformation amounts to this. Instead of integrating on the real line, you have a certain deformation like that. You change the domain like that, complex values, and you plot the solutions of this equation for k varying not on R3, on R, but on this deformed domain, and instead of having extended regions, you just have branch cuts. So you can say now, if you have branch cuts, we are in business because you can do what Feynman would tell you to do. how to calculate your amplitude in this point, for example. Feynman would tell you, you circumvent the branch cut from above, which corresponds to the Vic rotation. That's not what you have to do. Because if you do that, this branch cut will really lead to a discontinuity, an imaginary part in this kind of equation. You will have an imaginary part, because from above and from below you will have different results. You have a discontinuity. That is the imaginary part of the bubble diagram. But that means that you have a physical process, because it must be equal to that if you want unitarity. And this cannot be, because you have complex masses. So still, you have the problem. But now you are led to the solution, which is as follows. It's very simple, actually. So yes, it's true. If you deform this domain, you will shrink these awful extended regions, which have no meaning. They give no analyticity and no Lorentz invariance, to branch cuts. But you have a third possibility, and the third possibility is as follows. Compute your integral inside while the region is still extended. The result will not be Lorentz invariant and not analytic, you don't care. You compute your integral there, and then you shrink the region by deforming the domain. So you calculate inside and then deform the domain. So it's like calculating inside the cut. And there you have no discontinuity. Basically, you can prove a mathematical theorem also that tells you that the result is very, very simple. It's just the average of the two analytic continuations from above and from below. The arithmetic average. So this is a non-analytic operation to circumvent thresholds without having a physical process associated with it. And instead of a physical process, I call it a fake physical process, because you still have singularities, but normally violations of analyticity in amplitudes are associated with productions of particles. In this case, they are not. And if you want to see it as a Vic rotation, it's not an analytic Vic rotation, because a Vic rotation tells you to compute from in the Euclidean, and then if you analytically Vic rotate, you get Feynman, you go from above. I have to tell you to go from above and from below anytime you want to overcome these kind of thresholds. But once you know to do that, everything is fine. What is the result? If you plot it, for example, below the threshold you have a certain analytic function. Above the threshold you have another analytic function. And the singularity is this. There is no physical process associated with it, because this is the real part, but the imaginary part is 0, both below the threshold and above the threshold. In formulas, it's very simple. Feynman would give this, it's very familiar to you. Fakeon gives this. The fakeon gives this function instead of log z. Now, log z is an analytic function with a branch cut. This function is a function which forces you to break the complex plane into two disjoint regions, for example, region 1 and region 2, and then put a cut, for example, in the imaginary axis. And you have two analytic functions for two disjoint regions, like here. And the function in one region is non-analytically related to the function in the other region, but it is related to that in an unambiguous way by this formula. So basically, you have a new concept of analyticity in these kind of amplitudes. Normally, what do you have? Normally, you have two branch cuts, analytic Vic rotation, so you have the Feynman prescription, Analyticity means what? If you compute your amplitude in an open set, anywhere, by analyticity, you know it everywhere. Here, above those thresholds, let me blow those branch cuts into cones, because I am computing inside, so I had an extended region which I shrank, and then you can re-extend it to a cone, not necessarily anything you want, because what you're interested in is just the real axis in the end. So, but to make things visual, let me blow it up in a cone. So you have a disjoint region, and so you have one analytic function here and one analytic function there, which are these two. And the new notion of analyticity works as follows. If you compute your amplitude in any open set of the Euclidean region, not any region, the Euclidean region, with this unambiguous procedure, you can overcome every threshold and reach every other region and determine the analytic function here and in every other threshold. You cannot go backwards. You cannot go from here to the Euclidean region. And this solves the problem. Why? Because now the imaginary part of your bubble diagram is 0, because this quantization prescription is completely symmetric with respect to the reflection with respect to the real axis, while the Feynman prescription is not. So the Feynman prescription gives an imaginary part, but now the imaginary part is 0. That's why you can have 0 on the right-hand side by simply projecting those unwanted states away. So now the projection makes sense. But remember, we have changed some imaginary parts, and this changes the physics and all the physical predictions. So basically, instead of having that unacceptable optical theorem which we had before, which was like this. There was a sum on the right-hand side where instead of the completeness relation, you had a completeness, pseudo-completeness relation, something with plus or minus ones. Now with the new quantization prescription, you don't have plus or minus 1, you have 1 or 0. And the zeros are those that you can project away now, because naturally you get a completeness relation in the reduced space. And in the reduced space, you do have unitarity, because the imaginary parts here do not regenerate what you throw away. I have illustrated this in the bubble diagram because it's, first, it's a basic result, and everything can be done explicitly. If you want, you can check the generalization to all orders in this paper. So let's see what you can do for gravity. I guess you can understand it already. You can anticipate it by yourself, maybe. Take, for example, this higher derivative theory, cosmological term, Hilbert term, y squared and r squared. All coefficients are positive in this notation, alpha, zeta, and psi. You can add the standard model. Now, this theory has a ghost, and you can see it, for example, by eliminating the higher derivatives with extra fields, and then the action becomes as follows: Hilbert term for graviton, a scalar, Starobinsky scalar, I don't know, probably it deserves this name, with this kind of potential. This is fine, because its kinetic action has the right sign in front. But then you have a complicated action for a spin 2. The general formula is here. But if you expand it more explicitly and throwing away some non-minimal couplings and vertices, you will see that the quadratic part is a Pauli field with the wrong sign in front. That would be the ghost with the usual quantization prescription, but that just tells you that you have to quantize it as a fakeon. And when you quantize it as a fakeon, the theory is unitary. Remember that anything I said was valid for both signs in front of the propagator. So now you can ask, why can't I turn anything into a fakeon, even a massive scalar, or that I would consider physical? Yes, that you can do with some constraints. We will see that you can have only massive fakeons. You cannot turn the graviton into a fakeon, for example. That makes no sense for reasons we will see in a moment. But as long as your field is sufficiently heavy, it could be quantized as a fakeon, even if the coefficient has the right sign in front of the kinetic term. So phi, we don't know. It could be a fakeon or not. So basically, now you have a perturbative theory with which you can make any kind of calculation you normally make with the standard model, and to convince people that indeed you can, we did. Marco Pivo was my PhD student, now he's in the States, and we made a lot of computations based on this one-loop bubble diagram, mainly. So you have a graviton triplet, which is described by the graviton, a massive scalar which could be fake or not, and necessarily a fakeon or spin 2, which has this kind of mass related to the two parameters we saw before. For example, you can compute the bubble diagram and work out the resummation of the bubble diagram as something standard that you do, and calculate, for example, the width of the fakeon, chi mu. And it turns out that it is negative. So first result that points to something new here. You have negative widths. What is a negative width? It means that causality is violated at very short distances, 1 divided by the mass of chi. The mass of this field could be even smaller than the Planck mass. It could be 10 to the 12 GeV. Anyway, the time intervals involved in this are very short. Could be 10 to the minus 36 seconds. And I want to remind you that the shortest time we have ever measured directly is 10 to the minus 18. So we don't really know what time is below 10 to the minus 18. So basically, I'm considering this higher derivative theory because it's actually the unique strictly renormalizable theory I can build. It would be stellar theory if you quantize the fields a la Feynman, and then it would have ghosts. But now I change it into the right theory. The point is that you can use this one, but I prefer to eliminate the higher derivatives to make the various decomposition to simple poles explicit, and so you have these three fields. Sorry? Yes. Yes. So what is a negative width? It's nothing to be scared of. Basically, if you take a Breit-Wigner and you study the Fourier transform, you have this formula. The damping factor is always a damping factor. Gamma t is always positive because there is a theta function in front. The difference is that if you use this as a green function with a source and a response, when gamma is negative, the integral projects like that, from t to the infinite future instead of the past. With a damping factor, yes, still, if you're familiar with the Abraham-Lorentz force in classical electrodynamics, Jackson, this is that case. So in the end, if you put gravity together with a standard model, you have this family of fields, and the contributions of quantum gravity are the triplet, and this could be all the fields we need to explain everything. Now, you might raise this question: is there any other fakeon here? Because this prescription is so universal. Well, one thing, it cannot be applied to massless fields just because the violation of microcausality would turn into a violation of causality. Violation of microcausality takes place at distances 1 divided by the mass. So if the mass is 0, we won't have causality here.
Why did K just be?
Why what?
The boson K. G mu plus 2K in H mu. Because already H mu is already small with respect to the Gaussian part.
H mu is what?
Is already small.
H mu is a field.
Sorry?
H mu is the fluctuation of
Yes.
the metric.
Small with respect to eta mu. H mu.
Yes.
And what that K is this like that?
Oh, I have a redundant constant here, which is useful for... Yes, I have one redundant constant that is useful. It's like H bar. It's useful for me, for my... It's redundant. Put it to 1 if you want.
Dimension.
If you want, yes.
Okay.
It's just, I have one redundant constant. Yes.
So the mass is like the stellar mass. Still the stellar mass.
The same thing, yes. The mass is the same. So you can ask yourself if you can use this prescription for other fields of the table here. And now I tell you how to answer the question. Because first of all, a fakeon does not belong to a set of asymptotic states. So it's not in your spectrum. So technically, it's impossible to reveal it. But the point is that many of these fields have never been revealed directly. Well, of course, we see electrons. We can say we see photons. They actually only see photons because only photons come to our eyes. But certainly, we have never seen these things. So what you do is to produce them at CERN by colliding two things. They live a very short amount of time, and then they produce two other things, and then you plot everything. And when you make that plot, you see a peak, and the peak would be the same if it were fake or not. So that's not an answer to the question whether Z, for example, is fake or not. But let me tell you, let me remind you that I have messed with the imaginary parts of one-loop diagrams. And so that's where you have to go to see the difference. So basically, for example, let me study this plot. You will see that there is this deviation here, W plus W minus, and it starts precisely from this threshold, which corresponds to this bubble diagram, and the threshold is where the imaginary part starts to contribute, which is twice the mass of MW, not by chance. Now, if W were fake, the imaginary part would be different, and instead of having this, you would have maybe this or that. Okay, so you have a different kind of shape. And that's where you see the difference. You don't see any difference before at lower energies. So we can conclude that W is not a fakeon because of this. But the first bubble diagram to which the Higgs contributes is this one, and the threshold for the imaginary part was not reached by LEP2 because LEP2 stopped at 209 GeV, and this is 216. It should have been precise enough also, so probably could not see it anyway. Starting from that point, you should see a similar deviation, different in the two cases, Higgs fake or not fake. So the possibility that Higgs is fake is still open. LHC is much more precise and it can reach much higher energies than LEP, but is not equally precise. So who knows, probably the answer is already buried in the many data of LHC or not. It requires some work. Other applications are interesting here and concern the classical limit, which reveals some new features, because the starting classical action is not the classical action. Now you understand that we have been starting from a fake classical action, which I call actually entering classical action. Why is it not the classical action? Because it's unprojected. So the quantization tells you that you have to project away certain things, but you have to project away them classically as well. So what is the classical limit? The set of 3 diagrams, fine, but with no fakeon on the external legs, which means that you have to do something to go from the interim classical action to the true classical limit. And you can think of that as using a gauge fixed Lagrangian. That's a classical action. You do not take it as a classical action because it is unprojected. You have to unproject the ghosts and the temporal and longitudinal modes of the photon away. You don't do it. Why? Because it's local. It's very, very convenient to work with a local action. You do it only at the end. But the classical action is the projected one. Here the projection is very simple. The projection in the case of the fakeon is a new topic, and I'll tell you some results about that because it's opening new interesting things. Basically, what you should do is take the 3 field equations, solve the one of the fake with the fakeon prescription. You don't have any freedom here. It's not a degree of freedom. You don't have any freedom to choose boundary conditions, initial conditions for chi. You just have to use the fakeon prescription. And you insert the solution into the other 2. Well, funny thing is, let me give you an example here, for example, of the projection. Let me take a higher derivative non-relativistic theory. So you have a kinetic term, a force, and a higher derivative term. This is the equation of motion. You see that the kinetic part factorizes these 2. This is the fakeon, basically, and you invert it with the fakeon prescription. You move it to the right-hand side, and then you get an equation that instead of being ma equal f, is ma equal to some average of f, which is written here. And now you integrate not only from on the future, but on the past and on the future with this very, very rapidly oscillating function. And that is the reason why you have the violation of microcausality, even in the classical limit. So the violation of microcausality survives the classical limit. How to reveal its effects? We are studying implications of this in cosmology, and we are showing that to some extent the universe arranges itself so as to depress these violations even more, so it will be hard to detect them or amplify them. But I want to conclude with just a very simple remark. Since the theory I'm talking about comes from particle physics, basically, so it is perturbative quantum field theory, everything I have told you about is perturbative, including this projection. It's still not known how to make the projection non-perturbatively. And if you attempt to make it in, for example, in an interacting case, not with an external force, but with a self-interacting potential, you will generate, in the classical theory, all the features of quantum field theory. Asymptotic series, infinite. So instead of having higher derivative theory, you will have a theory with lower derivatives of infinitely many terms, with fastly growing coefficients. The solutions will behave precisely as asymptotic as you expect from an asymptotic series, namely, let's say the lowest order, not so good, the next order, fairly precise, the third order to the ninth order, all very precise. This is with a coupling constant equal to 110. And then after the 10th order, the theory becomes, the expansion becomes totally useless. Final comment is about the violation of causality. Should we renounce causality or not? I've never been a fan of causality, and if you want to understand why, read this part of Toft-Veltman diagrammas, where it explains to you that there is no definition of causality in quantum field theory. What we have is a definition due to Bogolyubov, And equivalently, Lehmann-Simancic, the one about commuting fields outside the light cone, those are not observable. They do not concern the S matrix. They do not talk about experiments. So it's very hard to fight for causality or elevate it to a fundamental principle. Time is over, I guess. 1 minute. If I have 1 minute, let me also comment on the other approaches to quantum gravity. Some referee complained that I was not mentioning the others, so I did it, but criticizing them all. And he was happy, so since then I do, I do it. Well, you know that you have these kind of approaches. This also tells you why I claim that my theory is the right theory. String theory, loop quantum gravity, holography are approaches that basically throw quantum field theory under the bus. That I think is really irresponsible. Asymptotic safety is instead an approach that is within quantum field theory. Its limits is that it is non-perturbative. Much better is an approach that it is perturbative. It is a quantum field theory. It admits a perturbative function. You can calculate everything with a comparable effort. You can couple to the standard model. And so as far as calculability, predictivity, and falsifiability, this theory bests the others by far. If you think a moment, it could be the most predictive theory ever, because it's predictive, it has two parameters, it could cover astronomical distances and get far below the Planck length. And so, you see, if you want to describe how physics proceeded, from classical mechanics down to the infinitesimally small, at some point, some people, I don't know why, but there are many things why you can speculate, decided they wanted to deviate away from the main path. This is just one step beyond the standard model. We do not have data about gravity, we do not have experiments. This is living in a fantasy world where you really decide that your intuition is able to understand what's there. So my bet was that quantum gravity is just the last mile of the path that led to the standard model. Thank you very much.
Example of a calculation you can do with your version of quantum gravity, which is impossible with usual non-normalized perturbative, non-normalized.
Yes, everything you want to calculate from energies equal to these masses, which I don't know what they are, but let's say some arguments 10 to the 12 GeV to the Planck mass and beyond, that you can do here. The non-renormalizable theory is good for low energies. That's fine. So anytime you stick to low energies, I'm a strong supporter, by the way, of non-renormalizable theories. They are fine. They work for probably for billions of years. They will be fine. But if you want to compute, or we will ever be able to envisage a situation, cosmological situation, where you need what happens at high energies, this theory allows you to compute it.
So this is the usual argument, perturbative non-linearity, grows with high energy.
Okay. Are you talking about the Froissart theorem? Yes. Okay, this is an interesting subject that I plan to study. There are limits on the growth of the cross-section for large energies. Those theorems are based on the existence of a mass gap. Okay, this is not maybe a big problem. And analyticity. Unitarity, the existence of a mass gap, unitarity and analyticity. Here I have a new notion of analyticity, so I'm not sure that it will still work. Some analysis shows that with no clash with the theorem, the cross-section might grow very fast, and I am not claiming that this theory has a nice ultraviolet behavior. I do not think it is asymptotically safe. Actually, I'm claiming, from the impressions I have, that you have a sort of asymptotic anarchy. Namely, in the limit of high energies, you really have something that is with no nice behavior, which is something, by the way, that I like.
Hi. So you could do this fakeon description for higher derivatives than you considered in gravity. You could also add higher derivatives to the standard model and fakeon them. And you have a lot of flexibility beyond what you found.
Yes. So if you add more higher derivatives to gravity or to the standard model, you run into what they specific are the Leibniz models, because this is not a Leibniz model. And what is their feature? It is they are super renormalizable. So in the realm of the super normalizable theories, you have infinitely many. And in the realm of strictly renormalizable theories, so if you want the gauge coupling for gravity be dimensionless, because the standard model tells us that all gauge couplings are dimensionless, then you have one theory. This is the situation.
Some years ago, Carl Bender and collaborators were working on Leibniz models, exactly related to different boundary conditions and different. Yeah. So I would like to ask if you see any connection between your approach and that, let's say, PT symmetric approach, and also, I mean, in '82, Stephen Hawking wrote that paper with the funny title of Two Separated Ghosts. So I think again the approach was concerning boundary conditions. I would like to comment on that point.
You probably are talking also about the works of Philip Mannheim, right?
Yes.
Yes, I had a long discussion with him at CERN in January. He has an approach which is very articulated, and the main difference between, he claims that he can make sense of the theory with these ghosts that in some way treats in a new fashion. The main difference between this approach and every other approach actually is that in every other approach there is no projection. They want to keep everything. I have doubts that you can make it work keeping everything as degrees of freedom. In some way here you freeze them, and yes.
Again, the